lord.
.10, 3.11, and we're planning to go up to 3.99.
99. What happens after 99?
Probably just 3.100 if we
100?
make it there.
Okay. And go all the way to 420. I got it. Forever Python v3. We'll talk about 4, but more for fun. So, 3.11 is coming out. One of the big sexy things in it is it'll be much faster. So how did you, beyond hiring a great team or working with a great team, make it faster? What are some ideas that makes it faster?
It has to do with simplicity of software versus performance. And so even though C is known to be a low-level language, which is great for writing sort of a high-performance language interpreter, when I originally started Python or C Python, I didn't expect there would be great success and fame in my future. So I tried to get something working and useful in about 3 months. And so I cut corners. I borrowed ideas left and right when it comes to language design as well as implementation. I also wrote much of the code as simple as it could be. And there are many things that you can code more efficiently by adding more code. It's a bit of a sort of a time-space trade-off where you can compute a certain thing from a small number of inputs, and every time you get presented with a new input, you do the whole computation from the top. That can be simple looking code. It's easy to understand. It's easy to reason about, that you can tell quickly that it's correct, at least in the sort of mathematical sense of correct.
Ready for battle.
Because it's implemented in C, maybe it performs relatively well. But over time, as the requirements for that code and the need for performance go up, you might be able to rewrite that same algorithm using more memory, maybe remember previous results, so you don't have to recompute everything from scratch. Like the classic example is computing prime numbers. Like, is 10 a prime number? Well, you is it divisible by 2? Is it divisible by 3? Is it divisible by 4? And we go all the way to, is it divisible by 9? And it is not, well, actually 10 is divisible by 2, so there we stop. But say 11 is divisible by 10. The answer is no, 10 times in a row. So now we know 11 is a prime number. On the other hand, if we already know that 2, 3, 5, and 7 are prime numbers, and you know a little bit about the mathematics of how prime numbers work, you know that if you have a rough estimate for the square root of 11, you don't actually have to check is it divisible by 4 or is it divisible by 5. All you have to check in the case of 11 is it divisible by 2, is it divisible by 3. Because take 12. If it's divisible by 4, well, 12 divided by 4 is 3, so you should have come across the question, is it divisible by 3 first? So if you know basically nothing about prime numbers except the definition, maybe you go for x from 2 through n minus 1, is n divisible by x? And then at the end, if you got all no's for every single one of those questions, you know, oh, it must be a prime number. Well, the first thing is you can stop iterating when you find a yes answer. And the second is you can also stop iterating when you have reached the square root of n, because you know that if it has a divisor larger than the square root, it must also have a divisor smaller than the square root. Then you say, oh, except for 2, we don't need to bother with checking for even numbers because all even numbers are divisible by 2. So if it's divisible by 4, we would already have come across the question, is it divisible by 2? And so now you go special case, check is it divisible by 2, and then you just check 3, 5, 7, 11. And so now you sort of reduced your search space by 50% again by skipping all the even numbers except for 2. If you think a bit more about it, or you just read in your book about the history of math, one of the first algorithms ever written down, all you have to do is check, is it divisible by any of the previous prime numbers that are smaller than the square root? And before you get to a better algorithm than that, you have to have several PhDs in discrete math. So that's as much as I know.
So, of course, that same story applies to a lot of other algorithms. String matching is a good example of how to come up with an efficient algorithm. And sometimes the more efficient algorithm is not so much more complex than the inefficient one. But that's an art, and it's not always the case. In the general cases, the more performant the algorithm, the more complex it's going to be. There's a kind of trade-off.
The simpler algorithms are also the ones that people invent first, because when you're looking for a solution, you look at the simplest way to get there first. And so if there is a simple solution, even if it's not the best solution, not the fastest or the most memory efficient or whatever, a simple solution, and simple is fairly subjective, but mathematicians have also thought about sort of what is a good definition for simple in the case of algorithms. But the simpler solutions tend to be easier to follow for other programmers who haven't made a study of a particular field. And when I started with Python, I was a good programmer in general. I knew sort of basic data structures. I knew the C language pretty well. But there were many areas where I was only somewhat familiar with the state of the art. Mm-hmm. And so I picked, in many cases, the simplest way I could solve a particular subproblem, because when you're designing and implementing a language, you have many hundreds of little problems to solve, and you have to have solutions for every one of them before you can sort of say, I've invented a programming language.
First of all, so CPython, what kind of things does it do? It's an interpreter. It takes in this readable language that we talked about, that is Python. What is it supposed to do?
The interpreter, basically, it's sort of a recipe for understanding recipes. So instead of a recipe that says, bake me a cake, we have a recipe for, well, given the text of a program, how do we run that program? And that is sort of the recipe for building a computer.
The recipe for the baker and the chef.
Yeah.
What are the algorithmically tricky things that happen to be low-hanging fruit that could be improved on? Maybe throughout the history of Python, but also now. How is it possible that 3.11 in year 2022, it's possible to get such a big performance improvement?
We focused on a few areas where we still felt there was low-hanging fruit. The biggest one is actually the interpreter itself. And this has to do with details of how Python is defined. So I don't know if the fisherman is going to follow this story.
He already jumped off the boat. He's
this.
I'm
bored.
gone.
Yeah.
This is stupid.
Python is actually, even though it's always called an interpreted language, there's also a compiler in there. It just doesn't compile to machine code. It compiles to bytecode, which is sort of code for an imaginary computer that is called the Python interpreter.
So it's compiling code that is more easily digestible by the interpreter, or is digestible at all?
It is the code that is digested by the interpreter. That's the compiler. We tweaked very minor bits of the compiler. Almost all the work was done in the interpreter. Because when you have a program, you compile it once and then you run the code a whole bunch of times. Or maybe there's one function in the code that gets run many times. Now I know that sort of people who know this field are expecting me to at some point say, we built a just-in-time compiler. Actually, we didn't. We just made the interpreter a little more efficient.
What's a just-in-time compiler?
That is a thing from the Java world, although it's now applied to almost all programming languages, especially interpreted ones.
So you see the compiler inside Python not like a just-in-time compiler, but it's a compiler that creates bytecode that is then fed to the interpreter. And the compiler, was there something interesting to say about the compiler? It's interesting that you haven't changed that, tweaked that at all, or much.
We changed some parts of the bytecode, but not very much. And so we only had to change the parts of the compiler where we decided that the breakdown of a Python program in bytecode instructions had to be slightly different. But that didn't gain us the performance improvements. The performance improvements were like making the interpreter faster, in part by sort of removing the fat from some internal data structures used by the interpreter, but the key idea is an adaptive specializing interpreter.
Let's go. What is adaptive about it? What is specialized about it?
Well, let me first talk about the specializing part, because the adaptive part is the sort of the second order effect, but they're both important. So bytecode is a bunch of machine instructions, but it's an imaginary machine. But the machine can do things like call a function, add two numbers, print a value. Those are sort of typical instructions in Python. And if we take the example of adding two numbers, actually in Python, the language, there's no such thing as adding two numbers. There's just the compiler doesn't know that you're adding two numbers. You might as well be adding two strings or two lists or two instances of some user-defined class that happen to implement this operator called add. That's a very interesting and fairly powerful mathematical concept. It's mostly a user interface trick because it means that a certain category of functions can be written using a single symbol, the plus sign. Mm-hmm. And sort of a bunch of other functions can be written using another single symbol, the multiply sign.
Ready for battle.
So if we take addition, the way traditionally in Python the add bytecode was executed is
It is
pointers, and more pointers.
ready for orders.
So first we have two objects. An object is basically a pointer to a bunch of memory that contains more pointers.
Pointers all the way down.
Well, not quite, but there are a lot of them. So
Yeah.
to simplify a bit, we look up in one of the objects what is the type of that object, and does that object type define an add operation? And so you can imagine that there is a sort of a type integer that knows how to add itself to another integer. And there is a type floating point number that knows how to add itself to another floating point number. And the integers and floating point numbers are sort of important, I think, mostly historically, because in the first computers, you used the same bit pattern when interpreted as a floating point number had a very different value than when interpreted as an integer.
Can I ask a dumb question here?
Please do.
Given the basics of int and float and add, who carries the knowledge of how to add two integers? Is it the integer?
Type.
It's the type integer versus...
It's the type integer and the type float.
What about the operator? Is the operator
A noble cause
just exist
requires
as a
noble
platonic
men.
form
Come
possessed
join
by,
our ranks.
by the integer?
The operator is more like it's an index in a list of functions
It's a great
that the
and
integer
glorious
type
time.
defines.
Fight for our cause.
And so the integer type is really a collection of functions, and there's an add function, and there's a multiply function, and there are like 30 other functions for other operations. There's a power function, for example. And you can imagine that in memory there is a distinct slot for the add operations. Let's say the add operation is the first operation of a type, and the multiply is the second operation of a type. So now we take the integer type and we take the floating point type.
We fight for you.
In both cases, the add operation is the first slot and multiply is the second slot. But each slot contains a function, and the functions are different because the add two integers function interprets the bit patterns as integers. The add to float function interprets the same bit pattern as a floating point number. And then there is the string data type, which again interprets the bit pattern as the address of a sequence of characters. There are lots of lies in that story, but that's sort of a basic idea.
I could tell the fake news and the fabrication going on here at the table. But where's the optimization? Is it on the operator? Is it the different
So
inside the integer?
The optimization is the observation that in a particular line of code. So now you write your little Python program, and you write a function, and that function sort of takes a bunch of inputs, and at some point it adds two of the inputs together. Now I bet you, even if you call your function 1,000 times, that all those calls are likely all going to be about integers, because maybe your program is all about integers. Or maybe
It's unfair they get to team up.
on that particular line of code where there's that plus operator, every time the program hits that line, the variables a and b that are being added together happen to be strings. And so what we do is, instead of having this single byte code that says, here's an add operation, and the implementation of add is fully generic. It looks at the object, from the object it looks at the type, then it takes the type and it looks up the function pointer, then it calls the function. Now the function has to look at the other argument and has to double check that the other argument has the right type. And then there's a bunch of error checking before it can actually just go ahead and add the two bit patterns in the right way. What we do is, every time we execute an add instruction like that, we we keep a little note of, in the end, after we hit the code that did the addition for a particular type, what type was it? And then after a few times through that code, if it's the same type all the time, we say, oh, so this add operation, even though it's the generic add operation, it might as well be the add integer operation. And the add integer operation is much more efficient because it just says, assume that A and B are integers, do the addition operation, do it right there in line, and produce the result. And the big lie here is that in Python, even if you have great evidence that in the past it was always two integers that you were adding, at some point in the future, that same line of code could still be hit with two floating points or two strings, or maybe a string and an integer.
It's not a great lie. That's just the fact of life.
I didn't account for what should happen in that case.
There.
In the way
Oh,
I
right.
sold the story.
There is some accounting for that.
And so what we actually have to do is, when we have the add integer operation, we still have to check, are the two arguments in fact integers? We applied some tricks to make those checks efficient. And we know statistically that the outcome is almost always yes, they are both integers. And so we quickly make that check, and then we proceed with the sort of add integer operation. And then there is a fallback mechanism where we say, oops, one of them wasn't an integer. Now we're going to pretend that it was just a fully generic add operation. We wasted a few cycles believing it was going to be two integers, and then we had to back up. But we didn't waste that much time, and statistically, most of the time, basically we're sort of hoping that most of the time we guess right, because if it turns out that we guessed wrong too often, or we didn't have a good guess at all, things might actually end up running a little slower. So someone armed with this knowledge and a copy of the implementation, someone could easily construct a counterexample where they say, oh, I have a program and now it runs 5 times as slow in Python 3.11 than it did in Python 3.10. But that's a very unrealistic program. That's just like an extreme fluke.
It's a fun reverse engineering task, though.
Oh, yeah.
So there's
People do that.
people like fun, yes. So there's some presumably heuristic of what defines a momentum of saying, you seem to be adding 2 integers, not 2 generic types. So how do you figure out that heuristic?
I think that the heuristic is actually, we assume that the weather tomorrow is going to be the same as the weather today.
So you don't need 2 days of the weather?
No. That is already so much better than guessing randomly.
So how do you find this idea? Hey, I wonder if instead of adding 2 generic types, we start assuming that the weather tomorrow is the same as the weather today. Where do you find the idea for that? Because that ultimately, for you to do that, you have to kind of understand how people are using the language, right?
Python is not the first language to do a thing like this. This is a fairly well-known trick, especially from other interpreted languages that had reason to be sped up. We occasionally look at papers about HHVM, which is for Facebook's efficient compiler for PHP. There are tricks known from the JVM, and sometimes it just comes from academia.
And so the trick here is that the type itself the variable doesn't know what type it is. So this is not a statically typed language where you can afford to have a shortcut to saying it's ints.
This is a trick that is especially important for interpreted languages with dynamic typing, because if the compiler could read in the source these x and y that we're adding are integers, the compiler can just insert the single add machine code, that hardware machine instruction that exists on every CPU, and ditto for floats. But because in Python you don't generally declare the types of your variables, you don't even declare the existence of your variable. They just spring into existence when you first assign them, which is really cool and sort of helps those beginners, because there's less bookkeeping they have to learn how to do before they can start playing around with code. But it makes the interpretation of the code less efficient, and so we're sort of trying to make the interpretation more efficient without losing the super dynamic nature of the language. That's always the challenge.
3.5 got the PEP 484 type hints. What is type hinting, and is it used by the interpreter, the hints, or is it just syntactic sugar?
So the type hints is an optional mechanism that people can use, and it's especially popular with sort of larger companies that have very large code bases written in Python.
Do you think of it as almost like documentation, saying these two variables are this type?
It is more than documentation. I mean, so
It's an ambush!
it is a sub-language of Python where you can express the types of variables. So here's a variable and it's an integer. And here's an argument to this function and it's a string. And here is a function that returns a list of strings.
But that's not checked when you run the code.
But exactly, there is a separate piece of software called a static type checker that reads all your source code without executing it and thinks long and hard about what it looks from just reading the code that code might be doing, and double checks if that makes sense if you take the types as annotated into account.
So this is something you're supposed to run as you develop.
It's like a linter, yeah. That's definitely a development tool, but the type annotations currently are not used for speeding up the interpreter. And there are a number of reasons. Many people don't use them. Even when they do use them, they sometimes contain lies, where the static type checker says everything's fine. I cannot prove that this integer is ever not an integer, but at runtime somehow someone manages to violate that assumption. And the interpreter ends up doing just fine. If we started enforcing type annotations in Python, many Python programs would no longer work. And some Python programs wouldn't even be possible because they're too dynamic. So we made a choice of not using the annotations. There is a possible future where eventually 3, 4, 5 releases in the future we could start using those annotations to sort of provide hints, because we can still say, well, the source code leads us to believe that these x and y are both integers, and so we can generate an add integer instruction. But we can still have a fallback that says, oh, if somehow the code at runtime provided something else, maybe it provided 2 decimal numbers, we can still use that generic add operation as a fallback. But we're not there.
Is there currently a mechanism, or do you see something like that, where you can almost add like an assert inside a function that says, please check that my type hints are actually mapping to reality? Sort of like insert manual static typing.
There are third-party libraries that are in that business.
So it's possible to do that kind of thing? It's possible for a third-party library to take a hint and enforce it? It seems like a tricky thing.
What we actually do is, and this, I think this is a fairly unique feature in Python, the type hints can be introspected at runtime. So while the program is running, I mean, Python is a very introspectable language. You can look at a variable and ask yourself, what is the type of this variable? And if that variable happens to refer to a function, you can ask, what are the arguments to the function? And nowadays you can also ask, what are the type annotations for the function?
So the type annotations are there inside the variable as it's at runtime.
They're mostly associated with the function object, not with each individual variable, but you can sort of map from the arguments to the variables.
And that's what a third-party library can do.
Exactly. And the problem with that is that all that extra runtime type checking is going to slow your code down instead of speed it up.
I think to reference this sales pitchy blog post that says 75% of developers' time is spent on debugging, I would say that in some cases that might be okay. It might be okay to pay the cost of performance for the catching of the type errors.
And in most cases, doing it statically before you ship your code to production is more efficient than doing it at runtime piecemeal.
Can you tell me about MyPy projects? What is it? What's the mission? And in general, what is the future of static typing in Python?
Well, so MyPy was started by a Finnish developer, Jukka Lehtosalou.
So many cool things out of Finland, I gotta say. Just that part of the world.
I guess people have nothing better to do in those long, cold winters.
Yeah.
I don't know. I think Jukka lived in England when he invented that stuff, actually. But MyPy is the original static type checker for Python, and the type annotations that were introduced with PEP 484 were sort of developed together with the static type checker. And in fact, Jukka had first invented a different syntax that wasn't quite compatible with Python. And Jukka and I sort of met at a Python conference in 2013. And we sort of came up with a compromise syntax that would not require any changes to Python, and that would let MyPy sort of be an add-on static type checker for Python.
Just out of curiosity, was it like double colon or something? What was he proposing that would break Python?
I think he was using angular brackets for types like in C++ or Java generics.
Yeah, you can't use angular brackets in Python. It would be too tricky for template.
Well, the key thing is that we already had a syntax for annotations. We just didn't know what to use them for yet. So type annotations were just the sort of most logical thing to use that existing dummy syntax for.
So
but there was no syntax for defining generics directly syntactically in the language. MyPy literally meant my version of Python, where my refers to Jukka. He had a parser that translated MyPy into Python by doing the type checks and then removing the annotations and all the angular brackets from the positions where he was using them. But a preprocessor model doesn't work very well with the typical workflow of Python development projects.
Yeah, it's funny. I mean, that could have been another major split if it became successful. Like if you watch TypeScript versus JavaScript, there's like a split in the community over types, right? That seems to be stabilizing now.
It's not necessarily a split. There are certainly plenty of people who don't use TypeScript, but just use the original JavaScript notation, just like there are many people in the Python world who don't use type annotations and don't use static type checkers.
No, I know, but there is a bit of a split between TypeScript and old school JavaScript, ES, whatever.
Well, in the JavaScript world, transpilers are sort of the standard way of working anyway, which is why TypeScript being a transpiler itself is not a big deal.
And transpilers, for people who don't know, it's exactly the thing you said with MyPy. It's the code, I guess you call it pre-processing, code that translates from one language to the other. And that's part of the culture, part of the workflow of the JavaScript community. So
that's right. At the same time, an interesting development in the JavaScript/TypeScript world at the moment is that there is a proposal under consideration. It's only a stage 1 proposal that proposes to add a feature to JavaScript where, just like Python, it will ignore certain syntax when running the JavaScript code. And what it ignores is more or less a superset of the TypeScript annotation syntax.
interesting.
And so that would mean that eventually, if you wanted to, you could take TypeScript and you could shove it directly into a JavaScript interpreter without transpilation. The interesting thing in the JavaScript world, at least the web browser world, the web browsers have changed how they deploy, and they sort of update their JavaScript engines much more quickly than they used to in the early days. And so there's much less of a need for transpilation in JavaScript itself, because most browsers just support the most recent version of ECMAScript.
Just on a tangent of a tangent, do you see, if you were to recommend somebody use a thing, would you recommend TypeScript or JavaScript?
I would recommend TypeScript.
Just because of the strictness of the typing.
It's an enormously helpful extra tool that helps you sort of keep your head straight about what your code is actually doing. I mean, it helps with editing your code. It helps with ensuring that your code is not too incorrect.
They're still growing.
And it's actually quite compatible with JavaScript. Never mind this syntactic sort of hack that is still years in the future. But any library that is written in pure JavaScript can still be used from TypeScript programs. And also the other way around. You can write a library in TypeScript and then export it in a form that is totally consumable by JavaScript. That sort of compatibility is sort of the key to the success of TypeScript.
Yeah, just to look at it as almost like a biological system that's evolving. It's fascinating to see JavaScript evolve the way it does.
Well, maybe we should consider that biological systems are just engineering systems too, right?
Yes.
Just very advanced with more history.
But it's almost like the most visceral in the JavaScript world, because there's just so much code written in JavaScript that for its history was messy. If you talk about bugs per line of code, I just feel like JavaScript eats the cake, or whatever the terminology is. It beats Python by a lot in terms of the number of bugs, meaning like way more bugs in JavaScript. Mm-hmm. And then obviously the browsers are developing. I mean, just there's so much active development. It feels a lot more like evolution, where a bunch of stuff is born and dies, and there's experimentation and debates, versus Python is more, all that stuff is happening, but there's just a longer history of stable working giant software systems written in Python, versus JavaScript is just a giant, beautiful, I would say, mess of code.
It's very different culture, and to some extent differences in culture are random, but to some extent the differences have to do with the environment.
Yeah.
And the fact that JavaScript is primarily the language for developing web applications, especially the client side, and the fact that it's basically the only language for developing web applications makes that community sort of just have a different nature than the community of other languages.
Plus the graphical component, and the fact that they're deploying it on all kinds of shapes of screens and devices and all that kind of stuff. It just creates a beautiful chaos. Anyway, back to MyPy. So what? Okay, you met. You talked about a syntax that could work. Where does it currently stand? What's the future of static typing in Python?
It is still controversial, but it is much more accepted than when MyPy and PEP 484 were young.
What's the connection between PEP 484 type hints and MyPy?
MyPy was the original static type checker. So MyPy quickly evolved from Yuka's own variant of Python to a static type checker for Python, and sort of PEP 484, that was like a very productive year where like many hundreds of messages were exchanged debating the merits of every aspect of that PEP. And so MyPy is a static type checker for Python. It is itself written in Python. Most additional static typing features that we introduced in the time since 3.6 were also prototyped through MyPy. MyPy being an open source project with a very small number of maintainers, was successful enough that people said this static type checking stuff for Python is actually worth an investment for our company.
Nice.
But somehow they chose not to support making MyPy faster, say, or adding new features to MyPy, but both Google and Facebook and later Microsoft developed their own static type checker. I think Facebook was one of the first. They decided that they wanted to use the same technology that they had successfully used for HHVM, because they had a bunch of compiler writers and sort of static type checking experts who had written the HHVM compiler, and it was a big success within the company. And they had done it in a certain way, sort of. They wrote a big, highly parallel application in an obscure language named OCaml, which is apparently mostly very good for writing static type checkers.
Interesting.
Yeah.
I have a lot of questions about how to write a static type checker then. That's very confusing.
Facebook wrote their version and they worked on it in secret for about a year, and then they came clean and went open source. Google, in the meantime, was developing something called PyType, which was mostly interesting because it, as you may have heard, they have one gigantic monorepo. So all the code is checked into a single repository. Facebook has a different approach. So Facebook developed Pyre, which was written in OCaml, which worked well with Facebook's development workflow. Google developed something they called PyType, which was actually itself written in Python. And it was meant to sort of fit well in their static type checking needs in Google's gigantic monorepo.
So Google was in one giant, got it. So just to clarify, this static type checker philosophically is a thing that's supposed to exist outside of the language itself. And it's just a workflow, like a debugger for the programmers.
It's a linter.
For people who don't know, a linter, maybe you can correct me, but it's a thing that runs through the code continuously, pre-processing to find issues based on style, documentation. I mean, there's all kinds of linters, right? It can check that. What usual things does a linter do? Maybe check that you haven't too many characters in a single line.
Linters often do static analysis where they try to point out things that are likely mistakes but not incorrect according to the language specification. Like, maybe you have a variable that you never use. For the compiler, that is valid. You might be planning to use it in a future version of the code, and the compiler might just optimize it out. But the compiler's not going to tell you, hey, you're never using this variable. A linter will tell you that variable is not used. Maybe there's a typo somewhere else where you meant to use it, but you accidentally used something else, or there are a number of sort of common scenarios. And a linter is often a big collection of little heuristics where by looking at the combination of how your code is laid out, maybe how it's indented, maybe the comment structure, but also just things like definition of names, use of names, it'll tell you likely things that are wrong. And in some cases, linters are really style checkers. For Python, there are a number of linters that check things like, do you use the PEP8 recommended naming scheme for your functions and classes and variables? Mm-hmm. Because like classes start with an uppercase and the rest starts with a lowercase, and there's like differences there. And so the linter can tell you, hey, you have a class that whose first letter is not an uppercase letter, and that's just, I just find it annoying. If I wanted that to be an uppercase letter, I would have typed an uppercase letter. But other people find it very comforting that if the linter is no longer complaining about their code, that they have followed all the style rules.
Maybe it's a fast way for a new developer joining a team to learn the style rules, right?
Yeah, there's definitely that. But the best use of a linter is probably not so much to sort of enforce team uniformity, but to actually help developers catch bugs that the compilers, for whatever reason, don't catch. And there's lots of that in Python. And so, but a static type checker focuses on a particular aspect of the linting, which, I mean, MyPy doesn't care how you name your classes and variables. But it is meticulous about when you say that there was an integer here and you're passing a string there, it will tell you, hey, that string is not an integer. So something's wrong. Either you were incorrect when you said it was an integer, or you're incorrect when you're passing it a string.
If this is a race of static type checkers, is somebody winning? As you said, it's interesting that the companies didn't choose to invest in this centralized development of MyPy. Is there a future for MyPy? What do you see as the, will one of the companies win out and everybody uses like PyType, whatever Google's is called?
Well, Microsoft is hoping that Microsoft's horse in that race called PyWrite is going to win.
PyWrite, right, like RIGHT?
Correct. Yeah, all my word processors tend to typo correct that as pyrite, the name of the, I don't know what it is, some kind of semi-precious metal.
Oh, right. I love it. Okay, so that's the Microsoft hope, but so let me ask the question a different way. Is there going to be ever a future where the static type checker gets integrated into the language?
Nobody is currently excited about doing any work towards that. That doesn't mean that 5 or 10 years from now, the situation isn't different. At the moment, all the static type checkers still evolve at a much higher speed than Python and its annotation syntax evolve. You get a new release of Python once a year. Those are the only times that you can introduce new annotation syntax. And there are always people who invent new annotation syntax that they're trying to push. And worse, once we've all agreed that we are going to put some new syntax in, we can never take it back. At least the sort of deprecating an existing feature takes many releases, because you have to assume that people started using it as soon as we announced it, and then you can't take it away from them right away. You have to start telling them, well, this will go away, but we're not gonna tell you that it's an error yet, and then later it's gonna be a warning, and then eventually 3 releases in the future maybe we remove it. On the other hand, the typical static type checker still has a release like every month, every 2 months, certainly many times a year. Some type checkers also include a bunch of experimental ideas that aren't official standard Python syntax yet. The static type checkers also just get better at discovering things that sort of are unspecified by the language, but that sort of could make sense. And so each static type checker actually has its sort of strong and weak points.
So it's cool. It's like a laboratory of experiments.
Yeah.
Microsoft, Google, and all, and you get to see.
And you see that everywhere, right? Because there's not one single JavaScript engine either. There is one in Chrome, there is one in Safari, there's one in Firefox.
But that said, you said there's not interest. I think there is a lot of interest in type hinting, right? In the PEP 484. Actually, like, how many people use that? Do you have a sense? How many people use? Because it's optional. It's a sugar.
I can't put a number on it, but from the number of packages that do interesting things with it at runtime, and the fact that there are like now 3 or 4 very mature type checkers that each have their segment of the market, and then there's PyCharm, which has a sort of more heuristic-based type checker that also supports the same syntax. My assumption is that many people developing Python software professionally for some kind of production situation are using a static type checker. Especially anybody who has a continuous integration cycle probably has one of the steps in their testing routine that happens for basically every commit is run a static type checker, and in most cases that will be MyPy. So I think it's a pretty popular topic.
According to this webpage, 20 to 30% of Python 3 code bases are using type hints.
This will be a fun one.
Wow, wonder how they measured that. Did they just scan all of GitHub?
Yeah, that's what it looks like.
Yeah.
They did a quick, not all of, but like a random sampling. So you mentioned PyCharm. Let me ask you the big subjective question. What's the best IDE for Python? And you're extremely biased now that you're with Microsoft. Is it PyCharm, VS Code, Vim, or Emacs?
Historically, I actually started out with using Vim, but when it was still called VI. For a very long time, I think from the early 80s to, I'd say 2 years ago, I was an Emacs user.
Nice.
Between, I'd say, 2013 and 2018, I dabbled with PyCharm, mostly because it had a couple of features. I mean, PyCharm is like driving an 18-wheeler truck, whereas Emacs is more like driving your comfortable Toyota car. That you've had for 100,000 miles, and you know what every little rattle of the car means. I was very comfortable in Emacs, but there were certain things it couldn't do. It wasn't very good at sort of, at least the way I had configured it. I didn't have very good tooling in Emacs for finding the definition of a function.
Got it.
When I was at Dropbox, exploring a 5 million line Python code base, just grabbing all that code for where is there a class foobar. Well, it turns out that if you grab all 5 million lines of code, there are many classes with the same name. And so PyCharm sort of once you fired it up and once it's indexed your repository was very helpful. But as soon as I had to edit code, I would jump back to Emacs and do all my editing there because I could type much faster and switch between files when I knew which file I wanted much quicker. And I never really got used to the whole PyCharm user interface.
Yeah, I feel torn in that same kind of way because I've used PyCharm off and on exactly in that same way. And I feel like I'm just being an old grumpy man for not learning how to quickly switch between files and all that kind of stuff. I feel like that has to do with shortcuts, that has to do with, I mean, you just have to get accustomed, just like with touch typing.
Yeah, you have to just want to learn that. I mean, if you don't need it much.
You don't need touch typing either. You can type with 2 fingers just fine in the short term, but in the long term, your life will become better psychologically and productivity wise if you learn how to type with 10 fingers.
If you do a lot of keyboard input.
But for everyone, emails and stuff, right? Like, you look at the next 20, 30 years of your life, you have to anticipate where technology is going. Do you want to invest in handwriting notes? Probably not. More and more people are doing typing versus handwriting notes. So you can anticipate that. So there's no reason to actually practice handwriting. There's more reason to practice typing. You can actually estimate, back to the spreadsheet, the number of paragraphs, sentences, or words you'll write for the rest of your life. You could, probably
Here we go again with the spreadsheet of my life. Huh?
Yes. I mean, all of that is not actual, like, converted to a spreadsheet, but it's a gut feeling. Like, I have the same kind of gut feeling about books. I've almost exclusively switched to Kindle now for ebook readers. Even though I still love, and probably always will, the smell, the feel of a physical book. And the reason I switched to Kindle is like, all right, well, this is really paving. The future is going to be digital in terms of consuming books and content of that nature. So you should let your brain get accustomed to that experience. And in that same way, it feels like PyCharm or VS Code. I think PyCharm is the most sort of sophisticated, featureful Python IDE. It feels like I should probably at some point very soon switch I'm not allowed to use anything else for Python than this IDE or VS Code. It doesn't matter, but walk away from Emacs for this particular application. So I think I'm limiting myself in the same way that using 2 fingers for typing is limiting myself. This is a therapy session. I'm not even asking questions. But I'm sure a lot of people are thinking this way, right?
I'm not going to stop you. I think that sort of everybody has to decide for themselves which one they want to invest more time in. I actually ended up giving VS Code a very tentative try when I started out at Microsoft and really liking it. And it took me a while before I realized why that was, but and I think that actually the founders of VS Code may not necessarily agree with me on this, but to me, VS Code is in a sense the spiritual successor of Emacs, because as you probably know as an old Emacs hack, the key part of Emacs is that it's mostly written in Lisp, and that sort of new features of Emacs usually update all the Lisp packages and add new Lisp packages. And oh yeah, there's also some very obscure thing improved in the part that's not in Lisp, but that's usually not why you would upgrade to a new version of Emacs. There's a core implementation that sort of can read a file, and it can put bits on the screen, and it can sort of manage memory and buffers. And then what makes it an editor full of features is all the Lisp packages. And of course the design of how the Lisp packages interact with each other, and with that sort of that base layer of the core immutable engine. But almost everything in that core engine in Emacs case can still be overridden or replaced. And so VS Code has a similar architecture where there is like a base engine that you have no control over. I mean, it's open source, but nobody except the people who work on that part changes it much. And it has a sort of a package manager and a whole series of interfaces for packages and an additional series of conventions for how packages should interact with the lower layers and with each other. And powerful primitive operations that let you move the cursor around or select pieces of text or delete pieces of text or interact with the keyboard and the mouse and whatever peripherals you have. And so the sort of the extreme extensibility and the package ecosystem that you see in VS Code is a mirror of very similar architectural features in Emacs.
Well, I'll have to give it a serious try, because as far as sort of the hype and the excitement in the general programming community, VS Code seems to dominate. The interesting thing about PyCharm and PHP Storm, which are these JetBrains specific IDs that are designed for one programming language. It's interesting to when an ID is specialized, right?
They're usually actually just specializations of IntelliJ, because underneath it's all the same editing engine with different veneer on top. Where in VS Code, many things you do require loading third-party extensions. In PyCharm, it is possible to have third-party extensions, but it is a struggle to create one.
Yes, and it's not part of the culture, all that kind of stuff.
Yeah, I remember that might have been 5 years ago or so. We were trying to get some better MyPy integration into PyCharm, because MyPy is sort of Python tooling, and PyCharm had its own type checking heuristic thing that we wanted to replace with something based on MyPy, because that was what we were using in the company. And for the guy who was writing that PyCharm extension, it was really a struggle to sort of find documentation and get the development workflow going and debug his code and all that. So that was not a pleasant experience.
Let me talk to you about parallelism. In your post titled Reasoning About Async I/O Semaphore, you talk about a fast food restaurant in Silicon Valley that has only one table. Is this a real thing? I just wanted to ask you about that. Is that just like a metaphor you're using, or is that an actual restaurant in Silicon Valley?
It was a metaphor, of course.
Okay. I can imagine such a restaurant. So for people who didn't read the thing, you should. But it was idea of a restaurant where there's only one table and you show up one at a time and you're prepared. And I actually looked it up, and there's restaurants like this throughout the world. And it just seems like a fascinating idea. You stand in line, you show up, there's one table. They ask you all kinds of questions. They cook just for you. That's fascinating.
It sounds like you'd find places like that in Tokyo. It sounds like a very Japanese thing. Or in the Bay Area, there are pop-up places that probably more or less work like that. I've never eaten at such a place.
The fascinating thing is you propose it's a fast food. This is all for a burger.
It was one of my rare sort of more literary or poetic moments where I thought I'll just open with a crazy example to catch your attention, and the rest is very dry stuff about blocks and semaphores, and how a semaphore is a generalization of a lock.
Well, it was very poetic and well delivered, and it actually made me wonder if it's real or not, because you don't make that explicit, and it feels like it could be true. And in fact, I wouldn't be surprised if somebody like listens to this and knows exactly a restaurant like this in Silicon Valley. Anyway, can we step back and can you just talk about parallelism, concurrency, threading, asynchronous, all of these different terms? What is it, sort of at a high philosophical level? The fisherman is back in the boat.
Well, the idea is if the fisherman has 2 fishing rods, since fishing is mostly a matter of waiting for a fish to nibble. Well, it depends on how you do it actually, but if you had if you're doing the style of fishing where you sort of you throw it out and then you let it sit for a while until maybe you see a nibble, one fisherman can easily run 2 or 3 or 4 fishing rods, and so as long as you can afford the equipment, you can catch 4 times as many fish by a small investment in 4 fishing rods. And so since your time, you sort of say you have all Saturday to go fishing, if you can catch 4 times as much fish, you have a much higher productivity.
And that's actually, I think, how deep sea fishing is done. You could just have a rod and you put it in a holster. You can have many rods. What is there an interesting difference between parallelism and concurrency and asynchronous? Is there one a subset of the other to you? Like, how do you think about these terms?
In the computer world, there is a big difference. When people are talking about parallelism, like a parallel computer, that's usually really several complete CPUs that are sort of tied together and share something like memory or an I/O bus. Concurrency can be a much more abstract concept where you have the illusion that things happen simultaneously, but what the computer actually does is it spends a little time running this program for a while, and then it spends some time running that program for a while, and then spending some time for the third program for a while.
So parallelism is the reality, and concurrency is part reality, part illusion.
Yeah, parallelism typically implies that there is multiple copies of the hardware.
You write that implementing synchronization primitives is hard in that blog post. You talk about locks and semaphores. Why is it hard to implement synchronization?
Because at the conscious level, our brains are not trained to sort of keep track of multiple things at the same time. Like, obviously, you can walk and chew gum at the same time because they're both activities that require only a little bit of your conscious activity. But try balancing your checkbook and watching a murder mystery on time. You'll mix up the digits, or you'll miss an essential clue in the TV show.
So why does it matter that the programmer, the human, is bad?
Because the programmer is, at least with the current state of the art, is responsible for writing the code correctly, and it's hard enough to keep track of a recipe that you just execute one step at a time. Chop the carrots, then peel the potatoes, mix the icing. You need your whole brain when you're reading a piece of code. What is going on? Okay, we're loading the number of mermaids in variable A and the number of mermen in variable B, and now we take the average or whatever.
I like how we're just jumping from metaphor to metaphor. I like it.
You have to keep in your head what is in A, what is in B, what is in C. Hopefully you have better names. And that is challenging enough. If you have 2 different pieces of code that are sort of being executed simultaneously, whether it's using the parallel or the concurrent approach. If, like, A is the number of fishermen and B is the number of programmers, but in another part of the code, A is the number of mermaids and B is the number of mermen, and somehow that's the same variable. If you do it sequentially, if first you do your merpeople computation and then you do your people in the boat computation, it doesn't matter that the variables are called A and B, and that is literally the same variable because you're done with one use of that variable. But when you mix them together, suddenly the number of merpeople replaces the number of fishermen, and your computation goes dramatically wrong.
And there's all kinds of ordering of operations that could result in the assignment of those variables, and so you have to anticipate all possible orderings.
And you think you're smart and you'll put a lock around it. And in practice, in terms of bugs per line per 1,000 lines of code, this is an area where everything is worse.
So a lock is a mechanism by which you forbid only one chef can access the oven at a time.
Something like that.
And then semaphores allow you to do what? Multiple ovens?
That's not a bad idea, because if you're baking cakes and you have multiple people all baking cakes, but there's only one oven,
Yeah.
then maybe you can tell that the oven is in use, but maybe it's preheating. And so you have to, maybe you make a sign that says oven in use. And you flip the sign over and it says oven is free when you're done baking your cake. That's a lock. That's sort of, and what do you do when you have 2 ovens, or maybe you have 10 ovens? You can put a separate sign on each oven, or maybe you can sort of, someone who comes in wants to see at a glance, and maybe there's an electronic sign that says there are still 5 ovens available. Or maybe there are already 3 people waiting for an oven, so you can't. If you see an oven that's not in use, it's already reserved for someone else who got in line first. And that's sort of what the restaurant metaphor was trying to explain.
Yeah, and so you're now tasked, you're sitting as a designer of Python with a team of brilliant core developers, and have to try to figure out to what degree can any of these ideas be integrated and not. So maybe this is a good time to ask, what is async IO, and how has it evolved since Python 3.4?
Wow, yeah. So we had a really old library for doing things concurrently, especially things that had to do with I/O, and networking I/O was especially a sort of a popular topic. And in the Python standard library, we had a brief period where there was lots of development, and I think it was late 90s, maybe early 2000s, and like 2 little modules were added that were the state of the art of doing asynchronous I/O, or sort of non-blocking I/O, which means that you can keep multiple network connections open and sort of service them all in parallel like a typical web server does.
So I/O is input and output, so you're writing either to the network, or reading from a network connection, or reading and writing to a hard drive, storage.
Also possible.
And you can do the ideas you could do to multiple while also doing computation. So running some code that does some fancy stuff.
Yeah, like when you're writing a web server, when a request comes in, a user sort of needs to see a particular web page. You have to find that page maybe in the database and format it properly and send it back to the client. And there's a lot of waiting for the database, waiting for the network, and so you can handle hundreds or thousands or millions of requests concurrently on one machine. Anyway, ways of doing that in Python were kind of stagnated, and I forget, it might have been around 2012, 2014, when someone for the umpteenth time actually said, these async chat and async core modules that you have in the standard library are not quite enough to solve my particular problem. Can we add one tiny little feature? And everybody said, no, that stuff is not to, you're not supposed to use that stuff. Write your own using third-party library. And then everybody started a debate about what the right third-party library was. And somehow I felt that there was actually a cue for, well, maybe we need a better state-of-the-art module in the standard library for multiplexing input-output from different sources. Mm-hmm. You could say that it spiraled out of control a little bit. It was, at the time, it was the largest Python enhancement proposal that was ever proposed.
And you were deeply involved with that.
At the time, I was very much involved with that. I was like the lead architect. I ended up talking to people who had already developed serious third-party libraries that did similar things and sort of taking ideas from them and getting their feedback on my design. And eventually we put it in the standard library. And after a few years, I got distracted. I think the big thing that distracted me was actually type annotations. But other people kept it alive and kicking, and it's been quite successful actually in the world of Python web clients.
So initially, what are some of the design challenges there in that debate for the PEP? And what are some things that got rejected? What are some things that got accepted that stand out to you?
There are a couple of different ways you can handle parallel I/O, and this happens sort of at an architectural level in operating systems as well. Like Windows prefers to do it one way and Unix prefers to do it the other way. You have an object that represents a network endpoint, say a connection with a web browser that's your client, and say you're waiting for an incoming request. Two fundamental approaches are:
Disengage!
Okay, I'm waiting for an incoming request. I'm doing something else. Come wake me up, or sort of come tell me when something interesting happened, like a packet came in on that network connection. And the other paradigm is we're on a team of a whole bunch of people with maybe a little mind, and we can only manage one web connection at a time. So I'm just sitting looking at this web connection, and I'm just blocked until something comes in, and then I'm already waiting for it. I get the data, I process the data, and then I go back to the top and say, no, sort of, I'm waiting for the next packet. Those are about the two paradigms. One is a paradigm where there is sort of notionally a thread of control, whether it's an actual operating system thread or more an abstraction. In async I/O, we call them tasks. But a task in async I/O or a thread in other contexts is devoted to one thing, and it has logic for all the stages. Like when it's a web request, like first wait for the first line of the web request, parse it, because then you know if it's a get or a post or a put or whatever, or an error. Then wait until you have a bunch of lines until there's a blank line, then parse that as headers, and then interpret that, and then wait for the rest of the data to come in if there is any more that you expect. That sort of standard web stuff. And the other thing is, and there's always endless debate about which approach is more efficient and which approach is more error prone, where I just have a whole bunch of stacks in front of me, and whenever a packet comes in, I sort of look at the number of the that there's some number on the packet, and I say, oh, that packet goes on this pile, and then I can do a little bit, and then sort of that pile provides my context. And as soon as I'm done with the processing, I can forget everything about what's going on, because the next packet will come in from some random other client, and it's that pile. And every time a pile is maybe empty or full or whatever the criteria is, I can toss it away or use it for a new space. But several traditional third-party libraries for asynchronous I/O processing in Python chose the model of a callback. And that's the idea, where you have a bunch of different stacks of paper in front of you, and every time someone gives you a new sheet, you decide which stack it belongs to. And that leads to a certain style of spaghetti code that I find sort of aesthetically not pleasing, and I was sort of never very successful, and I had heard many stories about people who were also sort of complaining about that style of coding. It was very prevalent in JavaScript at the time, at least, because it was like how the JavaScript event loop basically works. And so I thought, well, the task-based model where each task has a bunch of logic, we had mechanisms in the Python language that we could easily reuse for that. And I thought, I want to build a whole library for asynchronous networking I/O and all the other things that may need to be done asynchronously based on that paradigm. And so I just chose a paradigm and tried to see how far I could get with that. And it turns out that it's a pretty good paradigm.
So people enjoy that kind of paradigm programming for asynchronous I/O relative to callbacks. Okay, beautiful. So how does that all interplay with the infamous GIL, the global interpreter lock? Maybe can you say what the GIL is and how does it dance beautifully with async I/O?
The global interpreter lock solves the problem that Python originally was not written with either asynchronous or parallelism in mind at all. There was no concurrency in the language. There was no parallelism. There were no threads. Only a small number of years into Python's initial development, all the new cool operating systems like SunOS and Silicon Graphics IRIX, and then eventually POSIX and Windows, all came with threading libraries that let you do multiple things in parallel. And there is a certain sort of principle, which is the operating system handles the threads for you, and the program can pretend that there are as many CPUs as there are threads in the program. And those CPUs work completely independently. And if you don't have enough CPUs, the operating system sort of simulates those extra CPUs. On the other hand, if you have enough CPUs, you can get a lot of work done by deploying those multiple CPUs. But Python wasn't written to do that. And so as libraries for multi-threading were added to C, but every operating system vendor was adding their own version of that. We thought, and maybe we were wrong, but at the time we thought, well, we quickly want to be able to support these multiple threads because they seemed at the time in the early 90s, when they were new, at least to me, they seemed a cool, interesting programming paradigm. And one of the things that Python, at least at the time, felt was nice about the language was that we could give a safe version of all kinds of cool new operating system toys to the Python programmer. Like, I remember 1 or 2 years before threading, I had spent some time adding networking sockets to Python, and they were very literal translation of the networking sockets that were in the BSD operating system, so Unix BSD. But the nice thing was, if you were using sockets from Python, then all the things you can do wrong with sockets in C would automatically give you a clear error message instead of just ending up with a malfunctioning, hanging program. And so we thought, well, we'll do the same thing with threading. But we didn't really want to rewrite the interpreter to be thread safe, because that was like, that would be a very complex refactoring of all the interpreter code and all the runtime code, because all the objects were written with the assumption that there's only one thread. And so we said, okay, well, we'll take our losses, we'll provide something that looks like threads, and as long as you only have a single CPU on your computer, which most computers at the time did, it feels just like threads, because the whole idea of multiple threads in the OS was that even if your computer only had one CPU, you could still fire up as many threads as you wanted. Well, within reason, maybe 10 or 12, not 5,000. And so we thought we had conquered the abstraction of threads pretty well, because multi-core CPUs were not in most Python programmers' hands anyway. And then, of course, a couple of more iterations of Moore's law and computers getting faster, and at some point the chip designers decided that they couldn't make the CPUs faster, but they could still make them smaller, and so they could put multiple CPUs on one chip. And suddenly there was all this pressure about do things in parallel, and that's where the solution we had in Python didn't work. And that's sort of the moment that the GIL became infamous. Because the GIL was the solution we used to sort of take this single interpreter and share it between all the different operating system threads that you could create. And so as long as the hardware physically only had one CPU, that was all fine. And then as hardware vendors were suddenly telling us all, oh, you gotta parallelize. Everything's gotta be parallelized. People started saying, oh, but we can use multiple threads in Python, and then they discovered, oh, but actually all threads run on a single core.
Yeah. I mean, is there ideas in the future to remove the global interpreter log GIL? Like maybe multiple sub-interpreters, some tricky interpreters on top of interpreters kind of thing?
Yeah, there are a couple of possible futures there. The most likely future is that we'll get multiple sub-interpreters, which each run a completely independent Python program.
Nice.
But there's still some benefit of sort of faster communication between those programs.
But it's also managing for you this running of multiple Python programs. Like,
yeah,
so it's hidden from you, right?
It's hidden from you, but you have to spend more time communicating between those programs, because the attractive thing about the multi-threaded model is that the threads can share objects. At the same time, that's also the downfall of the multi-threaded programming model, because when you do share objects, you didn't necessarily intend to share them, or there were aspects of those objects that were not reusable, you get all kinds of concurrency bugs. And so the reason I wrote that little blog post about semaphores was that concurrency bugs are just harder. It would be nice if Python had no global interpreter lock and it had so-called free threading, but it would also cause a lot more software bugs. The interesting thing is that there is still a possible future where we are actually going to, or where we could experiment at least with that, because there's a guy working for Facebook who has developed a fork of CPython that he called the no-GIL interpreter, where he removed the GIL and made a whole bunch of optimizations so that the single-threaded case doesn't run too much slower, and multi-threaded case will actually use all the cores that you have. So that would be an interesting possibility if we would be willing as Python core developers to actually maintain that code indefinitely. And if we're willing to put up with the additional complexity of the interpreter and the additional sort of overhead for the single-threaded case. And I'm personally not convinced that there are enough people needing the speed of multiple threads with their Python programs that it's worth to sort of take that performance hit and that complexity hit. And I feel that the GIL actually is a pretty nice Goldilocks point between no threads and all threads all the time. But not everybody agrees on that, so that is definitely a possible future. The sub-interpreters look like a fairly safe bet for 3.12, so say a year from now.
A year. So the goal is to do a new version every year.
Yeah.
For Python. Let me ask you perhaps a fun question, but there's a philosophy to it too. Will there ever be a Python 4.0? Now, before you say it's currently a joke, and probably not, we're going to go to 3.99 or 3.99999. Can you imagine possible features that Python 4.0 might have that would necessitate the creation of the new 4.0? Given the amount of pain and joy, suffering and triumph that was involved in the move between version 2 and version 3.
Yeah, well, we as a community and as a core development team, we have a large amount of painful memories about the Python 3 transition, which is one reason that sort of everybody is happy that we decided there's not going to be a 4.0, at least not anytime soon, and if there is going to be one, we'll sort of plan the transition very differently. Because clearly we underestimated the pain the transition caused for our users in the Python 3 case. And had we known, we could have sort of designed Python 3 somewhat differently without making it